Hello again. Welcome back to the Neuro Symbolic Channel. I'm Paulo Shakarian, and today we have a little bit of a different video that we're going to talk about how to come up with ideas in artificial intelligence as well as how to evaluate those ideas. And I came up with this presentation for a class I'm teaching as we're getting ready to go into a phase in the class where students are engaged in a very serious project. And so the title of this little talk is How to Formulate Interesting Ideas in AI. But a lot of this is actually more general than that. You'll see what I mean in a moment. So here's kind of an outline, and we'll start with kind of oddly with what the government tells us. And I was in the government for many years early in my career, still deal with the government a lot in my work. And actually, the reason why I think this is important is people in government agencies, they think about things like, should I fund this project? Or should this patent be awarded? And they've actually thought deeply about what makes an idea original and have written it down. And so the first one I'll talk about is the Heilmeyer Catechism. And Heilmeyer was a director of DARPA, which is the Defense Advanced Research Projects Agency. For those of you who don't know, a lot of great computing ideas such as the internet, the SQL database, object-oriented programming can draw their roots back to DARPA. I've been funded by them in the past. Actually, I have current funding from them. Many of my colleagues do. A lot of great work gets done. But when you submit a proposal to DARPA, you have to cover this Heilmeyer Catechism. And the first starts out with, what are you trying to do? And can this be articulated in a way that doesn't use any jargon? Now, how you define jargon really depends on your audience because jargon within a group of AI researchers is going to be different from jargon for a general audience. But the point being is you want to simplify the language beyond your own purview of the world. And then how is it done today? And what are the limits of the current practice? And so if this is not a better mousetrap, but just a different mousetrap, that's not enough. If you're creating a startup, you could put, or if you're creating a company rather, you could potentially create a product that is not novel, but you can outcompete other companies based on things like price, better marketing, or creating a community around the product. Those things are nice in the business sense, but as scientists, we want to move beyond the existing approaches to things. So what is new in your approach and why do you think it will be successful? So you can think of this third item as having to do with what is the underlying scientific principle that is guiding us? What is leading us to do something new and novel? And what evidence do we have this will be better? So this doesn't imply that the research is already completed, but it does imply that we're going to invest in this research based on principles that we believe to be true based on what others have done before us. So this is why I can't go to DARPA and say, well, I want to make a time machine. Well, there's no evidence that I can create a time machine with today's science and technology. I wouldn't be able to write a good proposal for that. But I can go and say, hey, because we have recently discovered this certain phenomenon, we can build a system that has a given capability. Now, the trick here is you don't want things to be incremental. And so Incremental research means that, well, we're just going to advance a little bit beyond the state of the art. We're going to make some small tweak. And so you could think of something being incremental is that if we're essentially using the same science, but we're making a small adjustment. You could, if you're a machine learning person, you could think of, well, running this algorithm with a different hyperparameter or with a few more neural layers. Yeah, sure, maybe that might get you some improved performance, but any engineer dealing with the problem can think through that stuff. We want to move beyond the incremental. Who cares? If you're successful, what difference it will make? And so this is a big deal to DARPA because programs there have to have stakeholders. And so as we think of ideas, we have to think of the impact of who will be the other people that care. And so in certain areas, like say mathematics or theoretical computer science, a lot of the work in logic programming, if we have results that we want to be impactful to outside the field, we need to think of who else is going to care. And I name those fields of math and theoretical computer science and logic programming because they have a lot of possibility to, if I discover something there, I can impact whole other fields with that work. So you could imagine improvements to stochastic gradient descent, that would influence everyone who's training deep neural networks if you're successful in making such an improvement. And so this is the way to think about it. What is that broader impact? The next is what are the risks? And risks are something that often people don't do a very good job of thinking about because usually when we have an idea, we only think about a world in the future where our idea works, as opposed to thinking of, well, what are the risks in this? Would I spend a lot of money on this research and not discover anything? Or will it not just pan out because maybe I can't measure to the resolution I want, or the computer system I'm running this on doesn't have enough memory? And we have to be clear-eyed about our risks, and it's good to write them down and think through what those are. Uh, the next is how much will it cost? So we live in the real world and there are costs. And especially nowadays with computer science and artificial intelligence, costs can skyrocket. We can't just do arbitrary experiments. We have to be aware of things like the number of LLM calls, the use of cloud credits, the use of electricity. How long will it take? This is becoming more and more important in computer science, and I think that to do quality computer science research takes more time. A lot of us that when we started in the field are newcomers to the field, we tend to think, oh, we can just write code and we can move very fast. In order to get published in the top tier, you need to explore things a lot more thoroughly. And we'll talk later in this brief about some of the things that are specific to AI and machine learning. So that's another thing we have to be clear-eyed about. Just like cost, we have to be clear-eyed about time. Another thing with DARPA that's kind of interesting, what are the midterm and final exams to check for success? And DARPA programs are designed to do a lot of scientific work in a relatively short period of time, anywhere from like, say, 1 to 4 years. And throughout the course of that activity, there are metrics that we want to evaluate against. Now, granted, when we do new research, sometimes we might not have a clear idea of the metrics or the metrics may change. That's okay, but we should still have some targets. We should still have a plan on how we're going to measure performance. All right, so that's the Heilmeier Catechism. So now let's look at what the Patent Office says. So what are requirements of a patent? Well, first, it must be able to be used. So patents are more of an engineering thing than a scientific thing. So you cannot patent a theory. The patent actually has to be able to be used in real life. So the invention must work. You need to have a clear description of how to make and use the invention. And it has to be new or novel, something that is not done before. And this is something, worthy of some legal debate. And I'm serious about that because you have infringements and things like this. The other is non-obvious. So this kind of gets back to the comment I made with the DARPA stuff about not being incremental. So, what do I make of these? How does this impact scientific research? Well, we're really looking at two different viewpoints here. We don't have to be strict about adhering to all of these or all of these in an extreme way, but I think both are good to keep in mind. I think the Heilmeier Catechism clearly defines for us how to scope out a research effort, where the patent requirements force us to think a bit about what is uh, novel and unique about the technology that we are proposing. So these are ways to kind of evaluate what we're doing and to come up with plans. But what about coming up with ideas in the first place? And that's what we'll talk about next. And these are purely my own ideas. Some of them are influenced by other people. But this kind of, I mean, I guess my own ideas are like the way it's categorized. So if you don't like this field-focused, engineering-focused, or future-focused thing, leave a comment. Maybe you have a better idea. I just organized it this way for the slides. So field-focused. So to come up with new ideas, one thing I've observed over the years is if you're working in one field of scientific research, you can bring an idea from that field over to another. So an example here, I have a lot of friends who work on this thing called ACT-R. And the ideas there were ACT-R is a framework created based on principles from cognitive science, yet it's a system in computer science. So ACT-R is an example of bringing in an idea from a different field. Another way to think about things are seams within a field. So within computer science or AI, Neuro Symbolic AI grew out of a seam. You have the, KR people and you have the machine learning people. And how can you get these two things to work together? So that's one example of a seam, but there's many others. We can think of, say, the interaction between logic programming and human computer interaction. Logic programming could provide an explanation, but you actually need humans to actually read that explanation and make sense of it. So that would be another example of a seam. Okay, so to my next category here, we have engineering focused. So I have two bullets here. The first is picks and shovels. So this is causing us to think about what are the enabler technologies for a given task as opposed to directly performing that task. So here you could think of something like, well, you know, uh, maybe rather than focus on creating a new neural architecture, maybe I can come up with a way to better optimize the hyperparameters for my neural architecture. And that contribution of, say, some novel way of hyperparameter optimization can be used in, a variety of different cases, but it's not the problem itself. It's kind of like a meta problem, if you will. Another type of engineering focused research, that especially when I was at ASU was talked a lot about is use inspired. And, I think a lot about use inspired and going just beyond just, hey, this is an application. Applications are great, but I like to think of if it's true use inspired research, how do you tie that application back to the scientific principle? And so if I have a scientific principle and I have an application with that, applying that scientific principle in the real world, it's not going to work as advertised. So what are the shortcomings? Are there some assumptions made in that scientific approach that have been invalidated? And can we work to figure out maybe an extension to that scientific theory or a modification to it where now we can account for these real world things that we've been observing? And as we make those modifications, what in making those modifications is informing the underlying scientific principle? So it's more than ad hoc fixes. While those are interesting, if we can take the next step and those ad hoc fixes can inform something about the underlying science, now we've made a bigger contribution because we have a broader understanding. So the next category, and I'll talk quite a bit about this, is future focused. So can we imagine a future when something very hard is suddenly solved? So in the 1990s, when I was a kid, it was very hard to imagine everyone walking around with a very powerful computer in their pocket. Yet we have that today with our smartphones. And so no one would have thought about solving problems in the world where people had computers in their pockets. Now, there's two ways to think about this future focused here. And one could be, what does that mean when the technology reaches maturity? So going back to the smartphone example, what things can I understand when I'm able to have a smartphone in my pocket? What other problems does that raise? And so those will tend to be more technical. We could, from a business perspective, you could think, well, what if I drop it? Do I need insurance on it? Do I need a special case and so on? From a technical perspective, we could think of things like, how can that be more secure? Now that I have a computer in my pocket, how can I easily access large amounts of files? How can I interact with it in an easy way? The next thing is, what does it mean when the technology becomes widespread? So with the proliferation of technology, now we talk about not the case that you can just have a smartphone in your pocket. We can talk about the case where everyone has a smartphone in their pocket. And what does that mean? Everyone's now networked together. So what other things arise in that environment? With the future focused approach, we're trying to answer the question, okay, so what's next? And a way to approach answering this is to think about, the following thought question. So first is, does this technology have some fundamental limits? So there's been some work in the last 2 years, some researchers have written theoretical papers that suggest that LM hallucinations can't be solved with just scaling. Now, if you believe those results or you believe the assumptions behind them, what does this mean? And if you believe those assumptions, when are those assumptions violated, cause the conclusion to be different? And maybe how can we migrate over to that? Another thing to think about is, what are the security risks inherent to the technology? So this deals with security. We're talking about adversaries, and we're thinking about things like, what's the worst case threat? Is the paradigm itself inherently insecure? You can think about, the example I have there in the bullets is people in the 90s who thought about cybersecurity just as the internet was rolling out weren't providing much practical use then, because cybersecurity attacks were not really a big deal. But they were able to envision a future where, hey, as the internet became more widespread, how do we tackle these problems of security? What are the inherent flaws with the existing paradigm? And that's what led to a lot of enablers like HTTPS, secure Wi-Fi and stuff like that that we now have. What about safety? So as security addresses worst case, safety, we're talking about the non-adversarial case. So harm caused in the average. So what happens when we use our system and the weather suddenly changes? Or what if we're talking about a social technology and a at-risk population, such as young people or prisoners or people with mental disabilities get exposed to the technology. Some other things to think about in the future-focused approach is, what complexity is inherent in the technology? And I say complexity in terms of, you can think of this in terms of the structure of that technology, or you can also think of it in terms of computational complexity with the example here. It's like the transformer. It inherently requires quadratic space complexity for that network and the size of the input. That's a limiting factor. Just think, if you had started research on ways around that when the encoder architecture was introduced in 2017, you would have been on kind of the cutting edge of the research. Uh, you know, the other question here is, when does that technology require manual intervention? And sometimes we have to think really deeply. So like in logic programming, we tend to look over the fact that, hey, we always say we assume the existence of a logical language. With machine learning classification, we assume that there are some class labels in the training data set. Oh, where does that come from? It's often a manual process. So as you think up ideas, even before you start exploring them, have a little book. So, here's one I've been using lately. It's just a small notebook. I write it down. Some of you might use Google Docs or a tablet or whatever, but have some place where you write it down. And don't be afraid to socialize ideas with other people. Um, there's always concern someone may steal my idea. Yeah, that can happen. But and while that's, that can and does happen, but I firmly believe that I've gotten more out of sharing my ideas than what I've lost in other people, taking my ideas. And honestly, it happens very seldomly. Um, it's only, I'd say, a handful of times that it's happened to me in the last 20 years. If you create many ideas, evaluate them against each other. So kind of rack and stack. So is this one easier to implement? Does this one have a higher chance of success? What's their risk profile look like? And then think about, okay, doing a pilot. What is the smallest project that can provide evidence that this idea works? And then think about, well, what is the smallest project that maybe I could get a workshop paper, or the smallest project I could get a conference paper, the smallest project I could create a startup I could use for evidence to create a startup. This is like a nice way of thinking, because at the end of the day, doing pilots does cost time and usually money as well. Even though compute is relatively cheap, and more than any time, that I've been alive, we can get a lot of stuff for free or very low cost. It still is our time and our effort. We can't do everything. And so thinking about how to scope things, and we're trying to confirm or denial. I had an idea. These are the risks. These are some things that'll make it not work. I hope that the risk is very small. I hope it doesn't usually occur, but I don't know for sure. So I'm going to do an experiment to test to see if that risk exists, if the effect of my idea exists on a small scale, and that'll give me confidence, and maybe give me confidence to talk to other people about it and get their buy-in and help me explore this further. Trend following. So trend following is kind of the opposite of what I've been talking about. And you might hear the adage in the United States of kids chasing the soccer ball. And what this means is, when little children play soccer or football in other countries, they all run to the ball. Like, they don't play positions, they just kind of chase the ball. Everyone's excited to chase the ball. And we could think of researchers doing this. We can think of people who are chasing the soccer ball as opposed to creating something novel. And we see this in business too. We see venture capitalists all pile on the same topic. We see entrepreneurs creating, X number of startups that are all kind of the same and have very little variation. Are they all going to survive? Is there enough market for all of them? Doing something different is more challenging. It's more challenging intellectually because you have to think about it, and that's kind of what the last few slides were about to help you do that thinking. Well, one thing we haven't talked about is communication. When you're doing something new and different, communication is harder. When you start to not fit neatly into any category, you also need to think about how do I present this idea to others? And that's important as well. Okay, so the next we're going to start talking about approaches. So if you have your idea and now you're going to do this pilot, what are some approaches in the areas of artificial intelligence, machine learning, and data mining we can use? And so for many years, I did a lot of work in data mining. And what was interesting about that community was in the papers, often a great technique was to take a data set and kind of explore the aspects of that data set. Are there different relations between those variables? Are there certain ways of measuring variables that we can study? Can this give us insight into some kind of mathematical model, or maybe there's some kind of mathematical assumption I can make that's maybe not explicit, but it seems to work well with this data. So first you do a lot of exploring of the data. And this is a screenshot here is from a paper from a conference called ASONOM. And, we looked at social networks and we measured effectiveness in certain nodes causing viral cascades to spread in the social network. But then once you've done that study, then you can use that information from that study and you could say, okay, what are the properties? Can this lead to mathematical assumptions? Can it lead to heuristics? Can it lead us in a machine learning sense to engineer features? Can it even form the algorithms we're creating? And now you have an approach that's kind of rooted in the empirical aspects of the data. So these are not the empirical aspects of your own approach. These are the empirical aspects of the data. So we use the data to kind of inspire, what we're doing. And then the next step is, of course, to conduct thorough experiments, and we're going to go into a bit about that. This is a way of doing things. There's many others as well. But what's good about this is you're giving yourself permission to kind of explore the data. You're stopping first and taking the time to analyze. If we're doing a data-driven approach for a problem, this could be a nice way to do business. So as we look to evaluate methods, particularly within machine learning, accuracy, F1, these kind of things come up, right away. And so, of course, this is great measurement, especially if you can beat the state of the art. But you could think about other ways that you need to compare other than just, hey, we beat the state of the art. Are there different conditions? Does this hold up in different conditions? Of course, it's great to look at other data sets. And if you're into machine learning and you want to publish there, you have to look at very many data sets to show that your paper can be published. And this example is from a paper that actually was presented at EdgeCai workshop earlier this year. And what we did was we looked at, we noticed that the work we were building on made certain assumptions about, the overlap in the data and the sequential aspects. And so we compared against what they did in previous studies, and we beat that. But we also thought, hey, we don't necessarily agree with the assumptions these other people made. So let's look at other ways of doing this. Well, of course, we still have to include the way the prior work did it. But we also looked at other ways of doing the training test split and evaluated based on that as well. So precision and recall. So if you're doing a multi-class problem, especially if the classes are in balance, it's really important to look at these metrics by class, or at least by the target class, not when you just start looking at the micros or the macros, you lose information about the individual classes. And usually there's only, um, in the binary case, there's usually only one class you care about. In the multi-class case, there might be one class that does particularly well or poorly, and it's good to know that and understand what's going on. Understanding the split. So, I've always been against artificial splits because when you artificially create a balanced data set and then you train a model and then you go into the real world, it usually breaks. Um, but then on the flip side of that, knowing what that split is and knowing kind of your performance with respect to the split. So for example, if you have a precision of zero point 0.4 with a balance split, that's terrible. But if this is on a class that's like 1/100th of the data, that's actually quite good. So ablations are actually quite common. They're not just becoming more common. And so here we look at ablations with respect to different features. Um, in a lot of the more recent papers, we see ablations based on different components of the ML system. So we see in the neurosymbolic work like ABL, what happens when you ablate, the symbolic part of the system. What happens when if you have some reinforcement fine tuning, what happens when you ablate that? What happens when you replace, this novel algorithm I made with a standard thing for this one component. That's all really important because you really need to answer the question as to why this particular set of components together was used to solve this problem. Why couldn't something else off the shelf have been used to solve one of these components? And so you need to communicate that. So with ablations, you'll see that the performance should drop when you ablate away part of the system. Like you see in this, we had different feature sets that were used, and we see how performance actually decreases when we ablate those away. So this gives a little intuition as to what that particular component added. Rock curves, of course, oftentimes we get like a confidence score or a probability as part of the output to the model. So rock curves can allow us to get an idea of parameter sensitivity. Um, when you do this, you want to compare it with a no-knowledge baseline, which is just a diagonal line. In most ways, this is visualized. You should add error bars as shown here, which that will give your work more credibility. Also including the area under the curve, which is just a number that's exactly what it sounds like. And then the other thing is precision recall curves might be a good idea in some use cases as well. So we talked a lot about sort of accuracy numbers and dealing with that. Now let's talk about computational complexity and runtime. So if you have an algorithm, I think it's really important, especially now that you actually take the time to figure out the computational complexity of that algorithm. What I have found is that when you get especially into places where there's more machine learning reviewers and you introduce something like a rule learning algorithm or an inference algorithm, even if you think that looks trivial, that it's, linear runtime or constant, runtime or log n or whatever, others will question it because many people who are outside of the KR community are used to seeing that KR algorithms are very expensive, but this is not always the case. Oftentimes you could find a less expensive heuristic. So proving that, and saying that in the paper, I think is becoming very important. The other thing is it forces you to do that analysis. So a lot of times, if you write out the algorithm and you go back to your, Corman algorithms textbook, you might see, oh, well, I could really benefit from, some kind of data structure here, maybe like a heap or a queue or whatever. And I could drive my complexity down from n squared to n log n. Then you should do that, okay? And you should implement it that way. Because, complexity the computational complexity, you can't engineer that away. If that's the best the algorithm can do, you're not going to, this directly impacts into how well it can scale. Now, if you do the complexity result and then you have runtime analysis, it's a good idea to then go and plot how that complexity fits with your runtime and see how that compares. Usually very easy to do. You see some examples here. Now, if your complexity is very high, but you have like an algorithm that is doing KR stuff, a lot of times though, you could produce sound but incomplete results using what's called an anytime algorithm, where it just kind of spits out results that are parts of the solution or candidate solutions. And then you could just stop at any time you want, and you can say some guarantees about what was produced. So we could think, with something with deduction, for example, we could say, okay, well, as it runs, it starts listing all the atoms that are concluded from the knowledge base. We won't have all of them in a reasonable amount of time, but it can start producing some that, would be useful, and they would definitely be known to be true. And we could, so these algorithms we can then evaluate in a practical way based on accuracy or, like we have on here, number of anomalies discovered, et cetera, as a function of time. Now, speaking of KR, as we kind of look at things that depend on logic and rules, it's really important in a paper that if you have a target use case, to put examples of that logical language in the paper with English language explanations, because that will have the effect of making your work more concrete. So here we see some examples from the pretty old paper of mine. So what about your own metric? Why would you want to do this? Well, sometimes you might have something that's very domain specific, that's not covered by a standard metric. Sometimes the standard metrics may not make sense. So you should always consider having your own, but bear in mind you need to justify why you've come up with something special. In general, you want to keep it very simple. So here is a result from a paper we did at CIKM a while back, where we looked at fraction of searched area looking for missing persons. And we had some ideas about what this would look like if you had a dog versus not, because the dog could smell things, so it could have the effect of searching more area while traveling less than a person. And so, but looking at this fraction of searched area, that's not really a standard metric, but we wanted to show that this was somewhat stable with respect to our hyperparameter. Another example, this is from an abduction result. We actually looked at solution size, and here we're looking at solutions that had had a number of points. This was a geospatial abduction problem that were a certain distance from a cache. And so we came up with this measure, pretty easy to understand because it's all in terms of distance and quantities of things, but it made sense for this very application-specific problem. Finally, sometimes we will solve things as an optimization problem. And just for the sake of optimizing. So I did a bunch of work on community detection algorithms and social networks. And here we were looking at optimizing quantities that have already had a very solid intuition. And so the quantity we're optimizing, like that's the answer. So you can measure that as part of your results. And actually we do see this in machine learning as well, usually as a side result, and you see plots of the loss function, which shows the behavior of gradient descent or whatever you're using over the number of epochs or batches that you're going through. This is a little different in that we're looking at the quantity with respect to um, in this case, a hyperparameter value. So anyway, that's it for today. This was, again, just kind of a quick thing I did for this class. I thought some of the ideas were interesting and worth sharing. Well, let me stop sharing the screen. So yeah, I thought, I thought some of these ideas were worth sharing with the community. I think um, over the years and doing a bunch of different things, whether it's, patents or the startup I ran or, research, coming up with ideas is challenging but exciting and is also fraught with like difficulty because, I'll tell you right now, most of your ideas, just like most of my ideas, aren't that good. But if you get, I think it's a skill to generate ideas and to evaluate them, and that's kind of what I'm hoping to get across today. So if you like this video, please like and subscribe and support the channel. Thanks again for tuning in. Bye now.